suggestion on number 7 is instead of writing it as negative x cubed over 12, how would you write that?
Negative 12 x to the 3.
Plus x squared over 6 would be 1/6 x squared. X over 3 is 1/3 x. Okay, that way when you do the derivative, you don't have to do quotient rule over and over again. It's just a power rule. So 3 comes down, so we get negative 1/4 x squared. 2 comes down, so plus 1/3 x. Derivative of x is 1, so plus 1/3. All right, we need to figure out when this is 0 or undefined. My suggestion, what would happen if we took everything times a negative 12? Would that get rid of all of our fractions and make our first term positive? So I'm saying take our first derivative. We do need to remember what the first derivative is for finding the second. But let's multiply by negative 12 on both sides. So then we get 3x squared minus 4x minus 4. Then we can do slip and slide. Minus 6x plus 2. Divide our 3 back. 3x minus 2. 3x plus 2. So what are the critical points?
2 negative 2.
We use those to decide increasing, decreasing, max, and min. So if we make our sign line, we have a negative 2/3, positive 2, test points. So if you put in a negative 1, you get a negative times a negative, which is positive. 0 gives us negative times positive, which is negative. 3 positive times positive is positive. So we know it's increasing where this is positive, decreasing where it's negative. So it's increasing from negative infinity to negative 2/3 and 2 to infinity. Decreasing between the negative 2/3 and 2. Maxes and mins. At negative 2/3, you went from increasing to decreasing. So what happened right there?
Critical point, or is that a function?
Ooh, I have a mistake. I'm going to pretend I did that on purpose to make a good point. My increasing, decreasing is off. Do you know why? These are actually going to be flipped because my signs are all off. The very first step, what did I do to all this? I multiplied it by a negative. That changes those signs, doesn't it?
Mm-hmm.
So this is the reason I told you I wanted you to try this one, but I want to talk about it together. When you multiply by a negative, that means these signs are the opposite of what they would have been. So that's just kind of a word of warning. If you're going to do that, a better option is sometimes to factor out a greatest common factor, so you keep that negative trailing along. If you do choose to multiply by it to cancel it, you need to remember that and either go through and just flip all your signs or even come back up here and plug in before you multiplied by the negative. But that is the reason that it's better to factor out a greatest common factor, so you don't have to remember later on that your signs are all flipped. So this one's actually decreasing twice and only increasing in the middle. So when I go from decreasing to increasing, that's a local min. How do we find the y? Put it into the original, which is not beautiful. we get negative 10 over 81. Our local max happened right here when we went from increasing to decreasing. So if we put in a 2, negative 2/3. Okay, that's our increasing, decreasing, max, min. Now what do we need? Inflection point. So we come back and we do our second derivative. So I'm doing it from right here. Plus 1/3. We set it equal to 0. I multiply by negative 2, and we get 2/3. So that's our inflection point. For graphing purposes, you will need an ordered pair for that. If you plug that back into the original, you get 22 over 81. Okay, check our concavity, so 2/3 is where it changes, so smaller and bigger. And putting those into the second derivative, so if we put in a 0, we get a positive. If we put in a 1, we get a negative. So it's concave up from negative infinity to 2/3, and concave down after that. All right. Then we use all of this to draw a graph. So we said our min was at negative 2/3, negative 10 over 81. Just approximate it. Our max was at 2/3. Our inflection point, we mark those with an X, is at positive 2/3, 22 over 81. So right here. Okay, until we get to our minimum, our graph starts off decreasing, and it's curved upward until I get to my X. So decreasing, but curved upward looks like this. Okay, we have switched to increasing, but we're still curved upward. At this X, that's when my curve slightly changes, so now we're curving downward. When I get to here, then we start decreasing. So our graph looks something like this. The change in concavity a lot of times is not a drastic change, so that's why I'm having you mark an X there, so we can kind of tell that's approximately where we are flipping. Any questions there? Then let's get out that notes packet we were working on. I think we are ready for this one. So we are not adding anything new. We're just practicing like what I just did on that example, all of it, the graphing. So today I'll probably do these last two examples. We can get through them both. Tomorrow we're just going to practice some more, so it'll probably be a work day in class with some practice problems tomorrow and see how we're doing after that. Let's go ahead and look at this one. So here's my function, and I want everything, critical points, increasing, decreasing. max and min, inflection points, concavity, the whole bit. I won't be able to do absolute max and min unless I give you actual endpoints here. So if you had that information, you would do it. When I just have a function that's continuing forever, we're just looking for locals. So what do we have to do first? First derivative. All right, personally, I don't really want to multiply this whole thing out. We could. Can we just do product rule? That'd be good practice for us. So derivative of the first, so the 2 comes down, inside stays the same, subtract 1 from the power, so it's just the first, times the derivative of the inside, which is just 1. So derivative of the first one times the second, plus the first one. Derivative of the second, derivative of x minus 2 is just 1. All right, you can multiply all this out now. And certainly that's an option from the very beginning if you're more comfortable with that. I left it this way just to remind you of some factoring options. When I look at my 2 terms, what do both of them have in them?
X minus 1.
So let's take out an x minus 1. If I do that, I'm left with 2 times x minus 2 plus an x minus 1. Okay, you distribute and combine like terms, 2x plus x is 3x, minus 4 minus 1 is minus 5. So there's my first derivative. Can you tell me the critical points then? When that would be equal to 0?
1.
So now we can use this to find increasing, decreasing, max and min. Okay, so smaller than 1. In between 1 and 5/3, so maybe 4/3. Bigger than 5/3, so maybe a 2. So if I put in a 0, I have a negative times a negative, which is positive. If I put in 4/3, 4/3 minus 1 is positive. 4/3 times 3 is 4, minus 5 is negative, so positive and negative is negative. 2, positive and positive is positive. So what does that tell me?
Or you increase.
So we're increasing from negative infinity to 1, and from 5/3 to infinity. We are decreasing in between, from 1 to 5/3. All right, max and min. If you go from increasing to decreasing, what does that mean?
You have a local max or local min.
So we have the local max at 1 and the local min at 5/3. Okay, we are going to put these on a graph, so we need ordered pairs. Where do you have to put them in to get the ordered pairs? The original, because I want points on the actual graph. So if I put in a 1, 1 minus 1 is 0, so that's fine. If I put in 5/3, so 2/3, negative 4 over 27? Okay, so we've done our critical points, increasing, decreasing, max and min. All that's left is inflection points and concavity. So to get the inflection points, we're going back. We are looking at our first derivative and then doing the second derivative. Again, you could choose to FOIL that out first. I'm just going to do product rule. So derivative of the first one times the second plus the first, derivative of the second. x minus 8. So 5 equals 0. And we get 4/3, so that's our inflection point. We are going to ultimately mark this on a graph, so we will have to get the full ordered pair to do that. So if you plug 4/3 back into the original, -2/27. Do you guys know how I'm getting those? All right. Now, what do we find?
R equals, okay.
So we make our sign line. The 4/3, so smaller than 4/3 and bigger than 4/3. Okay, we're putting them into the second derivative. Make sure you keep track of where your derivatives are so you know where to plug it in. So if I put in a 1, I get a negative. If I plug in a 2, I get a positive. So that means my graph is concave down from -infinity to 4/3. Concave up, whoops, from 4/3 to infinity. Now we make a graph. I like to start by plotting any concrete points that I can. So start with your maxes and mins and any inflection points. Maxes and mins, we're just going to mark as a dot. Maxes, or inflection points, we'll put an X. So we had 1, 0. 5/3, -4/27. Okay. Obviously, this is really hard to mark because it's a very tiny number. We're just going to do the best we can here. So we have -4/27. At 4/3, -2/27, I have an inflection point. So that's right in between the two of them. So you can space out your y-axis a little bit more to give yourself more space if you need to. We know that our graph is increasing, decreasing, increasing. So now we just need the curve. When it starts off increasing, we have two options. It could be curving up like that, or it could be curving down like this. So that's where we look at the concavity. We are curving downward until we get to this x. So it's curving downward. Still curving downward. Very subtle change at that x where it's curving upward. And it's just going to keep going up and curving upward there. Questions on that one? So sometimes the hardest part is putting all that stuff together on the graph. Start with any concrete points. Think about your concavity last. All right, final example for today. Here's my function. 2/x², that's like 2x to the -2. Minus 1/x, that's like -1x to the -1, plus 4. You notice I did include something else here, vertical and horizontal asymptotes, because since x is on the bottom, it's not a polynomial. We will have those. We have done those before. It's just been a little bit. Do you remember how we found the vertical asymptotes? When the bottom is 0, so in this case x equals 0 is a vertical asymptote. Do you remember what we did to find the horizontal?
Or is that a? Oh, yeah, no.
Yeah, I think
Yeah,
you're
just-
thinking inverses maybe.
Yeah, I don't know.
We did the limit as we went to positive and negative infinity. I'm going to use it in fraction form. Because remember, we talked about these before Christmas. When you have x on the bottom, what's a number over infinity? That was my pizza example. If I have 2 pizzas and I invite more and more and more people in here, how much pizza are you getting? It's going to 0. Same thing with 1 pizza, going to 0. So this is 4, this limit is equal 4. So my horizontal is y equals 4. Homework for today won't have any asymptotes on it. We're going to work our way up to that. But I thought we could go ahead and look at one together that did. Okay, critical points. Now we're back to normal. We do our derivative. I'm going to do the derivative from the one where I wrote it with negative powers. So derivative of 2x to the negative 2 would be negative 4x to the negative 3. Derivative of negative x to the negative 1 would be positive x to the negative 2. If you prefer, you can write this as 4 over x cubed plus 1 over x squared. You need to know anytime this is 0 or undefined. You could multiply everything by x cubed. You get negative 4 plus x equals 0, so x equals 4. So the critical point is x equals 4. Is there another one?
Yeah. 0.
0, because it's undefined. Okay, so sign line. If I put a negative 1 into my derivative, so I would get a positive 4 plus 1, so that's a positive. If I put in a 1, I get a negative 4. Plus 1, so putting in negative. I put in a 5, get a negative 4 over 125 plus 1 over 25, which is positive. And you can certainly use a calculator if you need to on that. So we see it's increasing from negative infinity to 0, 4 to infinity. Decreasing between 0 to 4. Maxes and mins. At 0, increasing to decreasing, that should be a max. What happens when we plug 0 back into the original? It's undefined, so there is no max. Okay, at 4, I go from decreasing to increasing, so there's a min at 4. And if I plug that in, I don't think it's going to be real pretty. (31 over 8). Okay, now we need to do the second derivative stuff. So our second derivative, and I'm using my first right here to get there. So it would be 12x to the negative 4 minus 2x to the negative 3. Or 12 over x to the 4 minus 2 over x cubed. Set that to 0. Multiply by x to the 4th. So we get 6. So my inflection point, 6, is there another one? 0, because it's anywhere the derivative is 0 or undefined. Now, ordered pairwise, if we put in a 6 to the original, not real pretty, 35 over 9. Can you put 0 into the original? No, so it's not an actual point. Okay, then we check our concavity. Okay, so if I put in a -1, I get 12 plus 2, so that's positive. If I put in a 1, 12 minus 2 is still positive. If I put in a 7, I get a negative. Now, I cannot just say it's concave up from -infinity to 6. Does anyone know why?
Because you have a vertical asymptote.
Yes, since 0 is an asymptote, we do need to break it up from -infinity to 0 and 0 to 6. Concave down after 6. All right, that's all the stuff. Now we have to put it into a graph. Okay, asymptotes are dashed lines. So we have a vertical one at 0, horizontal one at 4. Our minimum was at 4, 31 over 8. So 31 over 8, that's just a little bit less than 4. And my inflection point is at 6, 35 over 9. All right, 31 over 8 is like 3.875, 35 over 9 is 3.88. It is just barely higher. Some of these changes are really hard to show on a graph. You're just giving me the best you can here. Use a decimal to approximate whatever you need to. So now we know our graph has to start out increasing and curving upward. So it's got to be rising and curving upward, and we kind of know asymptotes are just getting closer to without hitting. So that covers this piece. Okay, from 0 to 6, so until I get to my x, it's still curving upward, but my graph is decreasing until I get to 4. So it's decreasing, curving upward. That means I'm hitting this min, hitting this x. Now we're still increasing, but it's curving downward. So what's happening is you're just getting closer to this asymptote from the bottom there. Some of these points, I know, get really hard to graph because they're all so close together. I do try, like on homework tests and quizzes, to give you ones that are a little more spaced out, but I do want you to see how we handle that. All right, any questions there? Okay, so I wanted to do some problems out of the book, but to make life easier, I typed them up for you. So it's 4 questions on Google Classroom. The first 2, you're just finding the information, but you do not have to draw the graph. Okay, so just practice with that. Then there's one where I give you everything and ask you to draw a graph that meets the requirements, and the last one is where you do everything.